here with gases we've been talking about. So last time we got into gases and we talked about some important units of gases and kind of the big three as we talked about atmospheres, torr, and millimeters of mercury. There obviously are others like pascals, kilopascals, bar, PSI. But I would say, as I talked about last time, these are probably the major three that you usually will come across most of the time. And again, 1 torr is equal to 1 millimeter of mercury, and 1 atmosphere is equal to 760 torr, and also 760 millimeters of mercury. So that 760 number, as we talked about last time, is really the number that we use to do that conversion, to convert either from atmospheres to millimeters of mercury or torr, or backwards. We talked about some gas laws, and there's usually three types of variables that we deal with: pressure, volume, and temperature. We started with our friend Boyle there, who dealt with pressure and volume, and he kept temperature constant here. And that gave us Boyle's law, which is P1 V1 equals P2 V2, again at constant temperature. Sort of the relationship that we talked about is as the pressure goes up, we do see a decrease in the volume. Again, smaller volume, less room for everybody to fly around in, going to create a lot more collisions and a lot more pressure. And vice versa, as the pressure goes down, typically that's associated with an increase in volume. Again, larger volume, more room for everybody to fly around in, going to cause less collisions, and that's going to have us have our less pressure. We then saw Charles' law, which is a V1 over T1 equals V2 over T2. This is at constant pressure. And remember that in terms of Boyle's law in units, pressure, volume doesn't really matter what units they're in, as long as they're the same on both sides of the sort of equal sign. When we do get to gas laws, as we talked about, one of the consequences of what was found during sort of Charles' law by Kelvin was that pretty much all gases will end up at the same sort of temperature if you extend that line. And what that basically meant was that Kelvin there for pretty much every temperature. So any gas law that involves temperature should always be in Kelvin. Again, as we talked about, even if they sort of give you the numbers in Celsius, want the answer in Celsius, you do need to convert it to Kelvin and go into the gas law and then convert it afterwards. In terms of the volume here, it doesn't matter the units as long as they're the same on both sides. But again, definitely got to add that 273 to get it to Kelvin. What we saw here is as the volume goes up, that is corresponding to an increase in temperature. Again, when we increase the temperature, our gas molecules are going to be flying around faster. Because this is at a constant pressure situation, the way it's able to maintain the constant pressure is the volume will adjust accordingly, and that will keep the number of collisions pretty much the same. And that's what keeps basically the pressure basically constant in this situation. Same thing will happen if you lower the temperature. Again, our gas molecule is going to be flying around slower, which means we would normally see a decrease in the number of collisions. But what happens is the volume will also go down as well. And what that does, again, is keep the number of collisions sort of constant. And that's what keeps that pressure constant. So in sort of Charles' law situation, it is the volume that sort of adjusts to allow it to basically keep the constant pressure. And that doesn't happen in sort of Guy-Luszik's law that we also saw basically. And that is P1 T1 equals P2 T2. This is at constant volume. Now that means in this situation, same thing with our temperature, it doesn't need to be in Kelvin, but in this situation, because we do have a constant volume, it cannot adjust when we get those temperature changes. So in this situation, if the temperature goes up, we will directly kind of see a increase in pressure because the volume is fixed, it's a rigid container, and that means our gas molecules will be flying around faster, causing more collisions and more pressure. And if our temperature goes down, we will see the pressure go down again, because in this situation, they'll be flying around slower, volume is going to be fixed, and it will have less collisions basically happening. We also talked about rearranging these equations, which sometimes is problematic for people. But again, the quick way is anytime you go across the equal sign, just put it in the opposite location. So if it's on top, it goes to the bottom. If it's on the bottom, it goes to the top as you go across the equal sign. And that's a quick way you can rearrange these equations. Any questions on any of those there? All right, so we're in the middle of some examples. So I think we left off with this example. So why don't you do this one? We have an experiment with 452 milliliters of a gas in a light bulb. It's heated from 22 to 187. What is the final volume? Okay, let's take a look. Once again, as we talked about last time as well, really good approach where you're doing gas law problems again is just to pull out the information. So we have a volume that's 452 milliliters, goes with a temperature that's 22 degrees Celsius. We have another temperature that's 187, and we are looking for a volume. So again, if you just kind of roam through the gas laws that we saw last time, obviously, in this case, we have nothing to do with pressure as it's held constant. So you can kind of see Charles' law there is probably a good choice. We'll call these guys ones, these guys two. Remember that we do need to convert these guys into Kelvin. So we got to add a 273 to each of these. And that's going to give me 22 plus a 273, 295 Kelvin. 187 plus 273, 460 Kelvin. Now that we have that here, V1 T1 equals V2 T2. In this case, we're going to solve for V2, which means we need to move T2 to the other side, which means it will go up on top. V1 T2 divided by T1 equals our V2. Basically multiplying the T2 to the other side. Putting our numbers in correctly here, 452 milliliters. It is T2 that should be up on top for 60 Kelvin and 295 Kelvin here on the bottom. Kelvins will cancel, going to leave us milliliters as our units. And that's going to get us here. Looks like a 705. And this would be milliliters in this particular case. Once again, we can see that originally we're at 22 degrees Celsius. We went to 187, so our temperature went up. That means that our volume should follow, and it went from 452 to 705. So again, it does make sense based on what we should see as a result of Charles' law. Any questions on any of that calculation there? Okay, let's try one more here. Argon is inserted in light bulbs. Certain one contains 1.2 atmospheres at 18 degrees and is heated to 85 degrees. What is the final pressure in atmospheres? Let's take a look. Once again, pulling out the information here. 1.2 atmospheres is a pressure. That goes with a temperature that's 18 degrees Celsius. Again, we have another temperature at 85 degrees Celsius, and we are looking for a pressure. So once again, obviously this one's out. There's no volume, so you can hopefully kind of see Guy Lussick's law here. We'll call those ones and those twos. Like normal here, we're going to convert into Kelvin for our temperature. As we talked about last time, almost like a no-brainer kind of first thing you do. It's just if you have a temperature, convert it into Kelvin. So you'll be in good shape, and we'll do that there. 358. So again here, P1 T1 equals P2 T2. We're going to solve for P2. So we do need to multiply the T2 to the other side. That again is going to go to the top there. So P1 T2 T1 equals P2. Popping in our numbers again in the right spots. So P1, 120 atmospheres. T2 up on top, 358 Kelvin, and our 291 Kelvin on the bottom. Once again, Kelvin's going to cancel. In this case, it will leave us atmospheres up on top, which is good since we are looking for a pressure in this case. And that pressure looks like 1.48. atmospheres in this particular case. Once again, in terms of the temperature went up, and we would expect the pressure to go up, and again, it did in this case as well. Any questions on any of that there? Okay, so that is a few gas laws. Let's continue on then and talk about a few other ones. The next sort of gas law we're going to look at, or sort of gas relationship, comes from our friend, I think, Avogadro. He had a number, but he wanted a gas law as well, so why not? So when we think about Avogadro and Avogadro's number, we think about moles. And so it's not surprisingly enough that Avogadro's law here involves moles. It is V1 over N1 equals V2 over N2. There you go. And this is actually at two conditions, as it says here. This is at constant temperature and constant pressure. So under constant temperature and pressure conditions, the volume is sort of proportional to the number of moles of gas that's present. So V1 over N1 equals V2 over N2, N is the number of moles of our gas. And one of the consequences of Avogadro's law, or one way that you could use Avogadro's law, is pretty much like any other gas law. You could just plug and chug into the gas law there and solve for whatever is sort of present or you're looking for. A side sort of note of Avogadro's law is it actually can be used sort of in stoichiometry type problems. And if you should have a stoichiometry problem that's under constant temperature and constant pressure, and you have gases all involved, you could do a sort of stoichiometry problem like you do a mole to mole relationship, but you could actually do it sort of as a volume to volume relationship. So, for example, if we look at this equation here, and normally we would take our coefficients, and we could say, obviously, if we're looking at, say, the mole to mole relationship, just like we do in stoichiometry, we could go 3 moles of H2, 1 mole of N2, 2 moles of NH3. Now, because of Avogadro's relationship, if this was done under constant temperature and pressure conditions, and we were interested perhaps in how much volume of gas we would produce, we could actually do like a volume to volume relationship. We could say, for example, for every 3 liters of H2, we have to put in there 1 liter of N2. So we can kind of do a mole to mole relationship using volumes in this type of conditions. Again, it does need to be constant temperature and pressure to sort of do that. So if we look at one, for example, here, we want to know ammonia burns in oxygen to form nitric oxide and water vapor. We want to know how many volumes of NO is obtained from 1 volume of ammonia under constant temperature and pressure. So in this case, we're starting with 1 volume of ammonia. So that could be like 1 liter of ammonia. And we basically want to know how many liters, for example, of NO would we produce. So normally what you would have to do in this situation is if you had some values given to you, you could use a gas law a little bit down the road, do a little stoichiometry with moles to moles. But because this is under constant temperature and pressure, we could actually just do it sort of like stoichiometry. We could go to the equation, find NH3. We could also go there and find our NO. And we could say from that equation, for every 4 liters of NH3, we would get 4 liters of NO. And that means that we can use that as a sort of liter to liter sort of conversion and go with 1 liter of NH3. We would have 4 liters of NH3 gives us 4 liters of NO, in this particular case. Liters of NH3 will cancel, and you will end up with 1 liter of NO that would be produced. So this is a really nice relationship, especially if you're dealing with gases and you're looking for some type of volume at the end, and you know the volume of one of the other uh, substances in the equation. And it does, again, has to be at constant temperature and pressure. You could sort of bypass using a gas law and just kind of do a stoichiometry problem You could actually still use the gas laws. We'll talk about a little bit later on. We might see it again, but this makes it a little bit quicker to sort of do. So one of the consequences, again, of sort of Avogadro's law is you can kind of do this sort of volume to volume relationship under constant temperature and pressure, just as you could do a mole to mole relationship. Any questions on that? Obviously, you could do it with anybody here. It would be a 4 liter of NH3 for 6 liters of H2O, 5 liters of O2, 6 liters of H2O. So you can do all those same type of like mole to mole relationships. You can do volume to volume relationships. Any questions on that? Yeah. So putting all those gas laws together and looking at some of the relationships that we saw through these gas laws, we saw with Boyle's law again, as basically the volume increases, the pressure will decrease, and vice versa. Again, smaller volume, less room, more collisions, higher pressure, larger volume, more room for everybody to fly around, lower pressure. We saw with Charles' law again, the lower temperature, we need to kind of lower the volume to maintain that constant pressure. Higher temperature, we need a little bit more room for everybody to fly around in, again, to maintain that pressure. And as well here in a constant pressure situation, we do see, again, our temperatures increase or decrease along with the pressures. And with Avogadro's law with our moles. So kind of putting all these guys together gives us really sort of the granddaddy of them all, which is the ideal gas law. And putting that together gives us PV equals nRT, which is the ideal gas law. And it is the equation that's used for an ideal gas. And really, there's a couple of things that make something sort of an ideal gas. And really, kind of the two main aspects that make something an ideal gas is the idea that in an ideal situation, the volume of the gas itself is negligible compared to the container it's in or the volume of the container it's in. So if you look at a lot of problems that you do or come across, a lot of times what they talk about is not necessarily the volume of the gas itself, but it is the volume of the container that the gas is in. So whatever volume that container is in, it's assumed that that gas is going to fill it uniformly, and the volume of the container is more relevant in an ideal situation. Another sort of aspect that makes something sort of an ideal gas is the idea that under ideal conditions, you could have multiple gases together and they pretty much will not interact with one another. So there'll be no like attractive forces between the different gas molecules. There'll be no repulsive type forces during with the different gas molecules. So, and we'll see this when we talk about mixtures of gases. Even though you may have a mixture of gases under an ideal situation, you could almost assume like the gas is in there by itself. There's no other gas sort of involved. So those are really the two big things that make something an ideal gas. The volume of the gas itself is not important. It's really the volume of the container. And there is really no interactions between other gas molecules. No repulsive forces are sort of attractive forces. Most of the time, what we deal with is ideal gases. We assume ideal sort of behaviors. Towards the end of this chapter, we will talk about non-ideal conditions, and those happen at really large volumes and things like that. Are really high pressures, not volumes, but really high pressures. And then those conditions, you do have to take some things into account. So most of the time, we take an ideal gas, and under normal everyday sort of conditions of pressures and temperatures, we're usually pretty close to an ideal situation. And that's why we use the ideal gas law. The ideal gas law is just kind of a universal law because of that. It can kind of be applied to all gases and kind of useful. It is also the most restrictive in terms of the units that you use. When you use the ideal gas law, 100% of the time, the pressure needs to be in atmospheres. So whatever unit is in, it needs to be in atmospheres. Volume needs to be in liters. Moles should be moles unless something is seriously wrong. And like every other gas law, our temperature does need to be in Kelvin. The reason why pretty much all those guys need to be in those units is R. R is the gas constant, and R has a value of 0.08206, and it has units of liters times atmosphere divided by Kelvin times mole. Some people in some books will round this number these days to 0.0821. You can use whichever one you like. I use 0.08206 because that's what was beat in my head and I can't get it out. But a lot of books do round nowadays to 0.0821. The good news is, if you remember the gas constant there and the units that are associated with it, it tells you pretty much the units everybody else needs to be in the ideal gas law. And again, that's so everything cancels out correctly in this particular case. Also different about the ideal gas law is the idea it's kind of a one and done situation. So all the gas laws we looked at up until this point have like maybe two pressures, two temperatures, two volumes. This is just going to be basically one pressure, one temperature, that type of stuff. The other thing is you always have R available to you. So that's always a value that you have. It is very rarely given to you in problems. So they very rarely go, hey, the gas constant is this. They just assume that you know it and you have it available to you. So if you feel like you're missing something, that's probably the thing you're missing here to use the ideal gas law. Now, a couple of other important sort of aspects of sort of the ideal gas law and some other type of conditions is we'll start with STP. STP does stand for standard temperature and pressure. And when you are told something is at STP, it is actually giving you two values. One is the temperature is 273 Kelvin and the pressure is 1 atmosphere. So if somebody says this is at STP, those are basically the values that you should use for it. Yes. It is not. It's actually 273. Yeah. Normal everyday conditions is 25 degrees. Yeah. What's that? STP is at 273. It would be 0. Yeah. Other questions? Yeah. So normal everyday conditions, and is sometimes referred to as standard conditions. 25 degrees is kind of like normal everyday conditions. But in terms of gases, standard temperature and pressure is temperature at 273. Yeah. Other question? Okay, so there is a really nice relationship that does occur at STP conditions, and you do have to be at STP conditions for this relationship, and that is 1 mole of any gas at STP conditions is equal to 22.414 liters. So this is a conversion that you could use. Once again, it does need to be at STP conditions. So that means if your temperature is not 273 or your pressure is not 1 atmosphere, you should not use this. But the benefit of using this at STP conditions is it allows you don't have to necessarily use the ideal gas law. So you can kind of bypass the ideal gas law in a lot of calculations to use that conversion. But again, it has to specifically be at STP conditions to use that conversion of 1 mole is 22.414 liters. The good thing about it is if you don't even want to worry about that conversion, you 100% of the time could always just go into the ideal gas law and just put in 273 for the temperature, put in 1 atmosphere for the pressure, and it works. So you can use the ideal gas law for any conditions, STP conditions, non-STP conditions. It doesn't matter. You could just always go into that. But again, if you remember this conversion and it's STP, it can save you a little bit of work and sort of bypass the ideal gas law. That is, by the way, how we get to the gas constant. If you put in and solve for the gas constant from the ideal gas law, and you put in everything under STP conditions, which means your pressure is 1 atmosphere, 22.414 liters, 1 mole, and your temperature is 273, you get that 0.08206 number basically is, again, where all those units come from. All right, so let's try one here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a 5.43 liter at 69.5 degrees. Okay, so let's take a look. Once again, we're gonna kind of pull out the information. We're looking for a pressure. We have moles, which is 1.82. We have a volume that's 5.43 liters, and we have a temperature that is 69.5 degrees Celsius. Again, here, just kind of looking at the information, you could probably see the ideal gas law kind of popping out at you. Also, we do not have two pressures, two volumes, two temperatures, which we would need for all the other ones. We just need to make sure on units. Obviously, this is a mole, so that's good. The volumes in liters. We do, like everything else, need to convert our temperature into Kelvin. So we're going to do a 273 plus a 69.5. And that's going to give us a 342.5 Kelvin. Remember, never given to you usually, but you always do have your gas constant always available to you. And now we can use our PV equals nRT. In this case, we're going to divide our volume to the other side. Will give us pressure nRT divided by V. Putting in our values here, 1.82 moles are 0.08206 liters atmosphere Kelvin mole. And I'll go above it here, 342.5 Kelvin. Squeeze it in there. And we're going to divide all that by our volume, which was 5.43 liters. Our liters will cancel, our Kelvin will cancel, and our moles will cancel. It's going to leave us atmospheres left over in terms of the units coming from the gas constant. 1.82 times 0.08206 times 342.5 equals divided by 5.43, going to give us a pressure of 9.42 atmospheres in this particular case. Any questions on that one there? Now, I will say very common as well, in addition to, like we did here, converting our temperature into Kelvin. Also very common, you're given grams and you have to go to moles. And again, that's the molar mass, right, to do that. Also, I would say your liters and milliliters conversion is used a lot as well. So a lot of times you're given the volume in milliliters, you need to convert it to liters. So again, that's another sort of common conversion that you sometimes need to do as well. We didn't need to do it in this problem, but those are two spots where also you very commonly need to do some conversions before you go into the ideal gas law. Any questions on that there? All right, so why don't you try this? What is the volume in liters occupied by 49.8 grams of HCl at STP, hydrogen 1.008, Cl 3545? Okay, so let's take a look. In this case, we are looking for a volume, and we got 49.8 grams of HCl. Although that is not what we need in terms of units, we can definitely get some moles of that. So we do have N basically given to us. STP once again means that I have a temperature of 273 Kelvin. I also have a pressure of 1 atmosphere. So again, if you look at it, you got a P, a V, a N, and a T. So that could point you to the ideal gas law, PV equals nRT. Once again, we always have R, although not usually given to us in the problem. So that is, again, a value that we have. So we need to do a little bit of work here. We do need to convert our grams into moles, which again is a very common thing. In this case, just need to add those two together. It looks like 3646. So we'll convert our 49.8 grams of HCl into moles using the molar mass. We're going to put the grams on the bottom so they cancel. Moles up on top. So we end up with that. And we end up with 49.8 divided by 3646. 1366, we'll call it. 1.366 moles. So now we have really everything we need to solve for volume, which is what we're looking for. So we'll divide the pressure to the other side. V is equal to nRT over P. Putting in our numbers here, 1.366 moles are 0.08206 liters atmosphere Kelvin mole. Our temperature of 273 Kelvin, all divided by our 1 atmosphere. Atmospheres cancels, moles cancel, Kelvin cancel, is going to leave us here our volume in liters, 1 point, oops, come here, times 1.366 times 0.08206 times a 273. Going to give us about a, we'll call it 30.6 liters in this particular case. Any questions on that there? By the way, could I have solved this another way? I could have in this case. So because we were at STP conditions, this is where we could use that relationship of 1 mole is 22.414 liters, which means I could have just picked it up right about there and took my moles and used that as a conversion factor. And again, you could only do this because it is at STP conditions, and that should pretty much hit you the exact same answer of 30.6 liters. So this is again a situation where you could have done that. If you remembered, you can see you don't have to use the ideal gas law, but as you could also see, it works just as good with the ideal gas law, so it doesn't really matter which way you do it. Any questions on either of those there? Okay, then let's talk a little bit about some more gas laws because we don't have enough yet. So let's talk about what happens when, we kind of play with all 3 variables, our pressure, volume, and temperature. So when we play with our pressure, volume, and temperature, if we took really the ideal gas law and set it equal to R in 2 different situations, because R is the same value, that means you could then put these 2 guys equal to each other. And we get this gas law here, P1 V1 over N1 T1 equals P2 V2 over N2 T2. In most cases, though, we really don't kind of change the moles of gases, unless you open the top. So a lot of times this gas law is sort of reduced down to the bottom version of it, and it is sometimes referred to as the combined gas law. And that is P1 V1 over T1 equals P2 V2 over T2. Here, same rule, pretty much Kelvin for our temperatures. Pressures in this particular one doesn't matter. It could be any unit you want as long as they're, again, the same on both sides. And same thing with the volume here. It could be any unit you like as long as they're the same on both sides. So the combined gas law deals with obviously all 3 variables. Is also the one sometimes people have a very difficult time rearranging because there's a lot of stuff to rearrange sometimes. But if you need to invest time in learning these gas laws, which you do, I would say the combined gas law is probably the best one to know, along with the ideal gas law. So why I say that is, especially for example, if you want to remember this version of the combined gas law that actually has the moles in it. So for example, if you remembered P1 V1 N1 T1 equals P2 V2 N2 T2, and you come across a problem where there is no mention of moles. There's no mention of temperature, or temperature and moles are held constant, are not even mentioned. All you have to do is, scratch those guys out. And now what you're looking at is our friend Boyle's law. If you take that guy there, P1 V1 N1 T1 equals P2 V2 N2 T2, and you come across a problem where there's no mention of pressure or moles, or they're held constant, you just scratch those guys out on both sides, and now you're looking at Charles' law. If you take P1 V1 N1 T1 equals P2 V2 N2 T2, and you have no mention of volume or moles, or they're held constant, you just scratch those guys out. And now you have Guy-Lussac's law. And if you take P1 V1 N1 T1 equals P2 V2 N2 T2, and you come across a problem where you have both constant temperature and pressure. You scratch those guys out on both sides, and now you have Avogadro's law. So if you remember really, sort of your combined gas law, and again, whichever version you want to remember it, and the ideal gas law, you pretty much could get every other gas law that you would ever need. So it's a really good one to know. All you have to do is just scratch out what is held constant, what's not given to you in the problem, and you'll pretty much have the gas law that you need along the way. Any questions on how to do that there? No. All right, let's try one here then. Consider a sample of oxygen gas at 27 degrees Celsius with a volume at 9.55 liters and a pressure of 2.97. If we change pressure to 825 and heat it up to 125, what is the new volume of the gas? So we're getting in here. Take a look. We obviously have a temperature given to us of 27 degrees Celsius. That goes with a volume of 9.55 liters and a pressure of 2.97 atmospheres. The pressure then gets changed to 8.25 atmospheres. Temperature goes up to 125 degrees Celsius, and we are looking for a volume. So just by pulling out the information, it really should point you in the direction of the combined gas law, obviously, as it has all three variables involved. These guys will all be our ones. These guys will be our twos. And again, it really doesn't matter which ones or twos, as long as you keep the information together. We're going to add 273 here to get our temperatures into Kelvin. So 300 Kelvin and a 273 here, 398 Kelvin. In terms of other units, we're okay in terms of our pressures as they are both in atmospheres. Obviously, if one was like atmospheres, one was millimeters of mercury, you would need to do a conversion. So in this case, P1 V1 T1 equals P2 V2 T2. We're going to solve for T2. That means just very simply, we're going to move everybody to the other side that needs to be moved. Guy on the bottom will end up on top, and guy on top will end up on the bottom there when you do that. And that's multiplying and dividing that. That gives us P1, V1, T2 up on top, T1 and P2 on the bottom equals our V2. Again, we want to make sure we get everybody in the right spots. So we're going to go with P1 up on top, which is 2.97. We're also going to go with V1, which is 9.55 liters, and T2 up on top, 398 Kelvin, all divided by our T1, which is 300 Kelvin, and our P2, 8.25 atmospheres. Again, atmospheres on top and bottom will cancel. Kelvin on top and bottom will cancel. We will be left with liters as our units here. And if I get my calculator here, 2.97 times 9.55 times 398 hit equals, divided by 300 hit equals, divided by 8.25 hit equals. And that is a 4.56 liters, it looks like. Any questions on that one there? So again, like I said, this is the one that gives people a really hard time sometimes just rearranging it. So if that is a problem for you, you might want to take some time to make sure you know how to properly rearrange it. But again, the combined gas law, along with the ideal gas law, pretty much will give you every single gas law you'll ever need. So since you do need to know them, make sure you invest the time in perhaps remembering the combined gas law. And again, all you have to do is scratch out what is not given to you or what is held constant, and you'll have pretty much the gas law that you need. Any questions on any of that there? All right, we'll lay it up there for today.